All right, subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is section 17.3, which deals with electric circuits. Now, before we get into the details of these notes, I want to outline a couple of objectives that you should be able to meet by the end of this video. So objective number 1, be able to identify and determine what a closed circuit is. Objective number 2, determine the two ways that devices can be connected in a circuit. Objective number 3, determine what happens to the energy that charges have in a circuit. And the fourth and final objective is why, or be able to determine why, an overloaded circuit is dangerous. So let's start out here by talking about, well, what is an electric circuit? And an electric circuit is just defined as a set of electrical components connected in such a way that they provide one or more complete paths for the movement of charges. Now, with electric circuit, we need to be aware of two main types of circuits, one of which is a closed circuit. Now, a closed circuit is an electric circuit with a complete path and is connected across a source of voltage. Now, what's important to remember with a closed circuit is that electrons can flow in this closed loop path of a closed circuit. And if electrons can flow in this closed loop, that means that this closed circuit is going to allow charges to move and a current to be had in the circuit. Now, the other type of an electric circuit that we need to be aware about is known as an open circuit. And an open circuit is an electric circuit without a complete path and a source of voltage. Now, typically here, the source of voltage is normally an outlet that you would plug an electrical cord into. So we could also add this statement up here to our closed circuit. But in an open circuit, we have to remember that we have no charge flowing. And so if there's no charge flowing, that means that there is no current. Okay, so let's put this knowledge of the electric circuit to the test here in our example. And so our example here is just going to be a strand of Christmas lights. So typically here we have our picture, and I know it's a black and white picture here, but we have our Christmas lights here. They're plugged into that wall outlet here where we have the power cord, and the power cord is connected to all the light bulbs. And in this case, we're going to have two scenarios. The first is when the Christmas lights are plugged in and these bulbs are working or lit up. And so when this happens, what we have going on is this. The outlet that the string of lights are plugged into is the source of voltage. And if this is the scenario we're running here, and the outlet's working and the lights are working, the charges are going to move through the wires and the bulbs from one side of the outlet to the other. So again here, just to show this on our picture, we have one side of the outlet that is moving our current or our charges all the way through to the very end, and then it turns around and comes back through the other side and enters that other portion of the plug. That is that complete circuit that allows charges to flow, and in our case here, it's allowing electricity to flow through the outlet into the string of light bulbs and back to the other side of the outlet. Now, when this happens, all the bulbs are going to light up. Now, let's take it into scenario 2 where the lights are not plugged into an outlet, or let's say you have those old school lights where one of the bulbs aren't working. Now, when that happens here, either of these two scenarios, you either don't have the lights plugged into the wall socket there, or you have one of those bulbs removed in these old school lights, what happened is the circuit's not complete and no bulbs light up. Now I should add this here, getting a little advanced here for right now, but here in this set of Christmas lights, we are going to assume that the Christmas lights are strung or wired in what we call a series fashion. Now we'll learn why one bulb, removing one bulb in a series, would affect the flow of electricity in our examples. So now we can transition to some different parts of our circuits. So our first part that we are going to concentrate on are switches. And switches here, we have a particular kind of switch here in this picture, and that is a knife switch. You can kind of see it looks like a knife coming down on a chopping block. That's why we call it a knife switch. But a switch is just a device used to open and close a circuit. Now again, we need to talk about two scenarios with our switches. One of which is a closed switch. And when we have a closed switch, we are going to have a complete circuit. And this can be applied to an example here, and that is a light switch that we come into encounter on almost a daily basis. But when a light switch is in the closed position, it is going to turn on the light bulb and allow electricity or charges to flow through that particular wire. Now the other scenario that we need to talk about is an open switch. And so when we have an open switch, the circuit is broken. And so if we stick with our light switch example, this is going to turn off that light bulb. So now we can shift gears here to what I referred to earlier as a knife switch. And a knife switch here is seen in this picture that I'm holding up in the camera. And a knife switch is just a type of switch typically seen or used in a physics lab. And what the knife switch consists of is a metal bar cut across the conductor. So you can see the wires come into both sides. You have the metal bar, and you have that conducting business of that metal. Now what we also have in this knife switch is these wires, which you can see are connected there at the bottom. And these wires are places that connect to other devices in a circuit and allow that charge or electrons to flow from one place to the other in a switch. So we have two main scenarios that we need to talk about here with a knife switch. One is where we have the metal bar touching both sides of the switch. What this allows for is for electrons to move through the bar and reach the other side of the switch. And so in our example, in our picture here, if we have the switch that is closed, like we do in this example, and I know it's a black and white picture, but this is actually lighting up the light bulb in our example circuit. Now, I ran out of room here, but I want to talk about my second scenario, so I'm going to grab another sheet of paper here. So, our second scenario here with the knife switch is this. When we lift up on the metal switch of our knife switch, what this causes is the circuit to become open. And if we have an open circuit, we have no current. And to add on top of that, if we have no current, we're not going to light up the light bulb in the circuit. Okay, so now with that business here, kind of our basic terms of this section in mind, we can move on to some different topics here that are associated with circuits. So the first topic that we are going to get into more details is schematic diagrams. Now, schematic diagrams are defined as a graphical representation of a circuit that uses lines to represent wires and different symbols to represent other components. Now, here is a picture of a couple different schematic diagrams, really basic schematic diagrams, but you can see that we have some basic outlines of how we depict the wires and things like light bulbs in our diagrams. Now, these schematic diagrams are going to depict the construction of an electrical circuit or apparatus. Now, how it specifically depicts these things is by using pieces of the electrical circuit to be shown through designated symbols. Now, these schematic diagrams are the basis for how electricians wire houses or other appliances, and it should be noted that any electrical device can be represented by a schematic diagram. And this can be anything from things such as toasters or computers or even something as simple as a light switch in your house. And so just to show you an example here, here's a Google image I found, and this is the schematic diagram of a speaker. And you can see here just a simple speaker that you may find at a school or in an auditorium or something like that. Involves quite a bit of different symbols and devices to produce that sound out of that speaker here. So what we're going to do now is learn about some of these different types of symbols that we see in a schematic diagram. So it's very important that we understand and identify the different symbols that we've seen so far in a schematic diagram and be able to utilize those either from a picture or from a word description and draw it. So we can go kind of both ways on that category here. Now we should note that each element in a piece of an electrical equipment is represented by a symbol that reflects the element's construction or function. Now, the first symbol that we need to learn about here is a wire or a conductor. Now, a wire or conductor here, I'm going to draw a 90-degree angle, but a wire or conductor is just going to be represented by a single line here. Now, it should also be noted that wires are going to connect elements as conductors. Now, the next symbol that we need to represent is a resistor. And how we draw a resistor is we start out with a straight line, and then we make this zigzag pattern to represent that we have a resistor, and then we continue with a straight line. So again, it's represented by a zigzag line. Now, some people may refer to these zigzag lines as bends or multiple bends, and the bends indicate resistance in a straight path. So again, the bends are going to represent the resistance of a straight line path of a conductor. Now, the next element that we have to be aware of is a light bulb. Now, how we are going to show a light bulb is through a line that looks as such. So what we have here is a resistor, and we represent that it's a light bulb by putting a circle around it. Now, in some cases, some people may just consider a resistor a part of a light bulb. So in some circuit diagrams or some schematic diagrams, you may just see a resistor, and that is noting both either a resistor or a light bulb. And that is because a light bulb is a type of resistor. Now, specifically here, the winding filament in the light bulb is going to represent that resistor. The light bulb is going to resist or impede the movement of electrons flowing in that charge. And that's because it uses those charges or uses those electrons to make the light bulb be lit. Now, the next symbol that we have here is a battery or a direct current source. Now, how we draw a battery or a direct current source is by drawing a straight line, and then we draw a really tall perpendicular line, and just to the outside we label that with a plus sign. Now, next to this, not very far away, you can give it a little space, we draw another perpendicular line, and to the outside of that we represent that with a minus sign, and then we continue on with our straight line conductor or our wire. And so there's some things that we need to note here that are very important. Number one, the differences in line height indicates a voltage between positive and negative terminals in the battery. The taller line is the positive voltage, and the shorter line represents negative voltage. Now, there's one more symbol that I would like to go over. I need a new sheet of paper here. And that symbol is one of a switch here. So I'll change papers. And our last symbol we didn't have room for is a switch. Now, a switch can be drawn two different ways. The first way is as follows. And this way here that I've just drawn is an open switch. Now, a switch can also be drawn as being closed, and a closed switch looks like this. Now, it should be noted that the small circles indicate the two places where the switch makes contact with the wires. Now, most switches work by breaking only one of the contacts, not both. So in our case here, our closed circuit would open on that left-handed side circle. All right, so now that we have the business of schematic diagrams in mind, we can move on to some different types of circuits. Our first type of circuit that we can discuss about is a series circuit. And a series circuit is defined as a circuit in which the parts are joined one after another such that the current in each part is the same. Now, an example of a series circuit is seen in this picture here. And we're going to take this picture and actually make a series circuit here in this video. Now, it's important to know that in a series circuit, the path of the current is going to have a single pathway with the direction of those charges of flow. And so this is a really important statement because we have this. If we have a single pathway, again, that's really the very important part here. If we have a single pathway for the charges to flow, the current is going to be the same for each device in the circuit. Now, the amount of charge that enters the device is the amount of charge that exits the device. Now, with all of this in mind, the resistance of each object is going to be different. And so if the resistance of each object is different, really that means the voltage is different for each device. Now, another important point to make here with series circuits is that removing one element or piece along the path of a series circuit will cause the circuit not to work. Now, the reason that this happens is because if we remove one element, it's going to cause a series to be open for the whole circuit, and that's going to cause the circuit to fail. Now, oftentimes here, if we have a failed series circuit, it's important to know or identify where those breaks in those circuits could be. One break could be from an open switch, a burned out light bulb, or a cut wire. Now, the best way to see a series circuit in action is to actually set it up. So I'm going to pause the video and set the camera up to be able to show you this demonstration. So what I have in front of me here is a standard lantern pattern that you can buy from a typical store like Walmart. And then I have some alligator clips here, and these are functioning as my wires. And then I have it connected to a light bulb. Now these alligator clips, again, allow me to click onto the metal portions of the light bulb. And I'm going to show you one light bulb first. But as you can see, as I complete the circuit, so everything is connected together, the light bulb is shining. Now let me set up a series circuit with an additional light bulb. Okay, so I've added a second light bulb, and now I'm going to connect the two light bulbs together with an additional alligator clip. Now, as you can see here, both light bulbs are lighting up. Now, let's say that you have a burned out light bulb, and I'm going to simulate that by just shifting this. And let me shift that again. I'm just going to simulate that by just removing the light bulb, okay? So you can see what happened here. As I remove the light bulb, it causes a break in my circuit. So what's happening here is those electrons are flowing through and stopping where this burned out or where this removed bulb is. Now, if I put this bulb back in, this light bulb, I will get the lights to light up again. And that causes here, by replacing that light bulb, that causes the circuit to be complete again. And as a circuit is complete in a series circuit, what we can do is we can have those light bulbs light up again. So I'm going to pause here and we'll move on to a topic known as a parallel circuit. Now, a parallel circuit is defined as a circuit in which the parts are joined in branches such that the potential difference across each part is the same. Now, there's some important points to make here with parallel circuits. The first of which is that the voltage across each device is the same, but the current through each device can vary. What we have to keep in mind is that the sum of the currents in all devices needs to equal the total current in our circuit. Now, in a parallel circuit, it's important to keep in mind what the path of the electron is doing. So in a parallel circuit, electrons that are leaving one end of a battery or DC power source can pass through either bulb before returning to another terminal. Now, in this scenario here, I should have mentioned that we're dealing with this setup. So when I talk about the light bulbs here, that is in our setup. So if you want to hear or you want to add to this, see picture in notes. This is the picture I'm referring to. Now, with that in mind, the device with the least resistance will have more charge or electrons flow through it because the device offers less opposition to the movement of charges. Now, there's one more point that I want to make here with this picture, and I'm going to have to grab another sheet of paper here. But I'm going to have the picture here shown, and we'll talk about our final point. So utilizing this picture here that I've shown you, if we remove one light bulb in a parallel circuit, this would still allow charges to move through the other loop in the circuit. And the reason that this circuit can still have this flow of electrons is that it does not interrupt the flow of electric charge in other parts of the circuit. And really the bottom line for us is that one light bulb would still be lit. Okay, so to show you this example of a parallel circuit, again, I'm going to pause the video, set up the camera so that way I can show you what happens here. Okay, so for our parallel circuit, what we have here, again, same lantern pattern that we've been using. I already have an alligator clip hooked to the light bulb. And so what I'm going to do here is I am going to hook this up, and when I do this, obviously the light bulb lights because I connect the circuit. And so to make a parallel circuit, I'm going to take an additional alligator clip and I'm going to click it onto that alligator clip that's already there. Now, to my alligator clip, the other end, I'm going to connect it to this additional light bulb. And then I'm going to have my fourth and final alligator clip, and I am going to hook it to the other end of our non-lit light bulb. And finally, I'm going to come in here and I am going to have the light bulbs, you can see, light up because of this. Now, with our parallel circuit, it said, hey, if there's a break in one of these circuits, then one light bulb should still be able to light. So just like I did, I'm going to take out my light bulb here in the center, and as you can see, this light bulb here that is on the far side or closer to the camera here is still lighting. And I'm going to insert this light bulb back into our setup here, and you can see, hey, it lights again. Now, I could take out this light bulb here in the back, and again, the light bulb in the middle still lights. So one real advantage of a parallel circuit is even though one thing goes out, we can still continue the flow of electricity or the flow of charges to produce that power. Now, what I also want you to notice too is as I put the bulbs in, you can see that we have the different brightness. Okay, so again, the advantage of a parallel circuit here is if one thing goes out, then that doesn't mean the whole circuit is shut down. The circuit can still operate. So I'm going to pause the video and I'm going to get our next page of notes out. So one of our final parts here of section 3 is talking about electrical power. Now, electrical power is defined as the rate at which electrical energy is converted into other forms of energy. Now, an important concept of electrical power is that as charges move through a circuit, it loses energy. Some of this energy that is lost is transformed into useful work, like the turning of a motor. Now, other energy is lost in a form such as heat. Now, there's also a formula for electrical power. And that formula is our P for power is equal to our current, I, times our voltage. So again, to go over these particular items in our formula, P is for power, and the units for powers is in watts, or if you want to abbreviate that, just a capital W. Now, just as a reminder, a little side note here, that 1 watt is equal to 1 joule per second, or 1 amp times 1 volt. So it can be a joule per second or amp volt. Now, Our I is for current, and that is in the unit of amps. And remember, current can be expressed in amps, or we use capital A to represent amps. Now, our V is going to stand for volts. Now, as we're on electrical power, you may look at electricity bill someday in your life, and you'll notice that they express the amount of electricity that you used in kilowatt hours. And so what kilowatt hours are, what they're typically used for, is they're used for power companies to track the energy that's used in a location or in something like your home. Now, to put it into perspective here, 1 kilowatt hour, which we express as 1 kWh, 1 kilowatt hour, is equal to about 3.6 times 10 to the 6 joules. So it's kind of an important conversion, because we have talked about energy in the terms of joules, and this relates it to a kilowatt hour. And again, kilowatt hour can have the notation or shorthand method of kWh. Now, let's go ahead, let's put this formula to the test, and let's go ahead and solve in our next example. So in this example, it says, hey, a hair dryer, which is a typical thing that is used fairly often. A hair dryer is plugged into an outlet that has 120 volts. If the hair dryer has 9.1 amps of current in it, we want to know what is the power rating of the hair dryer. Well, again, with our formulas, hopefully you've realized this, we write down what we have as our formula. So P equals I times V, and your P is your power. So that's going to be our question. Our I, in this case, is going to be the current, which is 9.1 amps. And then your V is the amount of volts, and this is plugged into a standard 120 volt outlet. Now, we have everything that we need to be able to find power, so we take P equals our amps, which is 9.1 amps, times our 120 volts. And when we do this here, we would take 9.1 times 120, and we would get a amount of power of 1092. Now, this right here would be equal to our watts. So that hair dryer would have a power output here of 1092 watts. Okay, so one of our final parts here is going to be talking about overloaded and short circuits here. So kind of a concept here that goes hand in hand. And so we start out here with an overloaded circuit. Well, an overloaded circuit is just when electrical wires carry more than a safe level of current. And an overloaded circuit is going to occur when many devices are connected across an electrical outlet and the overall resistance of the circuit is lowered. Now, the dangers of an overloaded circuit is this. The high current in an overload circuit could cause a fire. Now, a short circuit is another term here associated with this electric current. And so with a short circuit, this is going to happen when two wires touch and create an alternative pathway for current. Now, the danger here is that it's going to lower the resistance and increase the current within the wire. And an example of this, it can be caused by worn insulation on wires. Now, a classic example of a short circuit is if you have those jumper cables with your car and you accidentally touch the ends after you've plugged one portion into the battery of an on car. What happens, you see the sparks light up. Well, that is a short circuit. Essentially, those wires touch and you get that big spark. So that's why it's important to keep those separated until you're getting ready to actually jump those cars here. Okay, so with this here, we can prevent short and overloaded circuits by using fuses and circuits. Okay, so remember, overloaded circuit, you plug too much stuff into one outlet. Short circuits, two wires touch, causes those sparks. These things can be prevented via fuses and circuit breakers. And that's our last part of notes here for this electricity unit. All right, so fuses. We start out here with fuses. And these are defined as an electrical device that contains a metal strip that melts when current in the circuit becomes too great. And I have a picture here of a fuse, and you can see here they have this metal strip, and the one picture here on the left, this is a fuse that has been burnt, and so it would prevent electricity from flowing through that. But with our fuses, it's going to contain that ribbon of wire with a low melting point. Now, if the current in a particular line becomes too large, the fuse melts and the circuit is open. So if we have a 20 amp fuse, that means that when the circuit exceeds 28 amps, the fuse will melt, and we call that a blown fuse. Again, a 20 amp fuse will melt when the circuit exceeds that 20 amps, and this is what we refer to as a blown fuse. Okay, so now circuit breakers. These are defined as a switch that opens a circuit automatically when the current exceeds a certain value. And so these are usually in these boxes here, and usually in a home or a house here, they'll have a certain room with the circuit breakers. And you may hear your parents refer to this as a circuit has blown, and they have to go reset this, okay? And so what a circuit breaker is going to contain is a metallic strip with two different metals welded together. Now, these bimetallic strips respond to current overload by opening the circuit. Now, what we can also talk about here with circuit breakers is what we have commonly known as a ground fault circuit interrupter, or a GFCI. So you may see a GFCI in places like a bathroom or a kitchen where there may be water, and you have that risk of dangerous electricity associated with that. And so a GFCI here, if I can zoom in on the picture, looks like this. And so it's an outlet here, and it's a special kind of outlet that acts as a small circuit breaker. All right, so that is all the information contained in our section 17.3, where we dealt with electrical power and electrical circuits. And this is actually our last set of notes for our electricity unit. So I hope you have enjoyed this video. And as always, if you haven't already, make sure you subscribe.